delay. It is a pleasure to have Jacqueline Horn here. As you'll see, today is made up of three separate lectures that each give a bit of a perspective on different aspects of neuroimaging data science. Jacqueline Horn has been in neuroimaging data science for even before data science was a word, I guess, and thought a lot about this, and it's great to have his perspective as well to add to the others that you'll hear today. And it's a pleasure to have him here. Thanks so much.
Thank you, Aaron. Thank you, everybody. So I'm really delighted to come here to Seattle, to the University of Washington, to take part in this year's NeuroHackademy. I'm a local. I grew up on a small island just over there where you have to take a ferry boat to get there. And that is one of my favorite places in the world. It's so beautiful here. You're probably, if you're from out of town and you're not familiar with Seattle, you've probably heard a lot about how much it rains here. Well, today you're in luck because I made some calls. And so I think I've made some arrangements for you so that you have a great week here. I'm hoping that that weather sticks around for the weekend in case you want to take in some of the seafair festivities that are going on around town, which is very exciting. I want to talk a little bit about just some of my perspectives that I've kind of accumulated over the years and kind of digested and thought a little bit about and share them with you in terms of big data, smaller data, data that is kind of deep and data that is wide, and what the considerations for modeling and inference in relation to neuroimaging might be. Some of what I'm going to talk about overlaps quite nicely with the words that we heard from earlier from my friend and colleague, Russ Poldrack. We kind of, have been interacting with each other. We're colleagues. We've published together for a number of years. And so some of these same ideas come up, but I think that in the spirit of what we're talking about today and what you'll be doing over the next couple of weeks, this is entirely appropriate. And I hope you'll appreciate that in the spirit which it's meant, because there's some things that I think are just worth saying twice. Let's see here. There we go. So just to introduce things. So many of you, like me, got excited about brain research because of the complexity, of the dimensionality, of the opportunity for collecting data in this space and then doing something useful with that data. Depending on where you look, the argument is, and I think we like to tell ourselves this a little bit, but the argument seems to exist that the staggering complexity of the brain is so great, it is greater than that of the complexity of the known universe. And there, depending on where you look and online and in various kind of print media, this gets kind of recapitulated over and over again, that the brain is the most complicated thing in the universe. We're struggling to try to understand it, but we're getting closer. And through some of these data science methodologies and whatnot, we're now trying to decode it, read people's mind. And as a consequence of this, we continue to collect more and more data. Oops, too far. Sorry. We continue to collect more and more data. What has happened over my career is that when I was about where you guys are now, my laboratory director asked me to go and buy the hard disk for our laboratory that was going to store all of our big data. This was like, 30 something years ago. I went out and I bought the largest freestanding SCSI hard disk that you could buy at the time, and it was 4 gigabytes. And I thought, this is infinity. I will never fill this up, right? This is so vast. And people would come by the lab just to gaze upon this thing. I was like, wow, Jack, that's so cool. And it was so big. And of course, now, each of us could eat 4 gigabytes for breakfast. It's nothing, right? And it's really kind of interesting. The growth of this cycle of data multiplication, if you will, has really just kind of accelerated with all of these large-scale data initiatives, data sharing efforts and whatnot. So our data has gotten large, and it's gotten large for a number of different reasons, one of which is the advances in the neuroimaging technology. When I started in MRI, before we even started in MRI, we had like a 1.5 Tesla machine. The 1.5 Tesla was the standard, and then it was 3 Tesla. Now it might be 7 Tesla or higher, but that gave us the ability to gather more data. With every technological quantum leap, we were able to get more data per unit time and per unit of space. Our resolution got better and we could collect it more quickly. And when I remember a senior colleague once telling me, I don't think you'd ever want to collect any bold data faster than a TR of 4 seconds, because it's there's just not much information in there. And now we're sub-second TRs. We have like super high sub-millimeter resolution. It's really quite crazy. This allows us to ask more enhanced and more nuanced neuropsychological and neuroscientific questions. So we become more curious about what's going on in these smaller timescales or these smaller spatial scales. We collect more data per unit of time and per unit of space. That fills up those hard disks that you're buying or you're paying for through your Google or Amazon accounts. Because people aren't satisfied with that, we start this idea of collecting data from across multiple sites. So we're like asking the University of Washington to partner with the University of Virginia to collect more data so we can do this at scale. This allows us to collect more data, but it also means we've got more storage considerations, right? That 4 gigabytes is not going to cut it anymore, right? We're going to need something bigger. And then as we do this and we're starting to analyze that data, our questions get more nuanced again, and we ask ourselves even more nuanced questions, and we would have a desire to collect more data. At the same time, MRI physicists are earning their paychecks by figuring out how to dial the scanner up, how to increase the windings on the scanner to collect still more data per unit of time and space. As a consequence of all this whole thing going on, data gets big. We are now collecting data at really quite impressive rates. And whether or not you're looking at the Human Connectome Project, ABCD, the UK Biobank, or whatever, that scale of data collection is much more than it ever was when I was where you are now. So I've been on record as saying that neuroimaging has grown as a big data science when we have hopefully this works here. When we have advanced scanner technologies, we've advanced our analytic capabilities. This hunger for more data has really driven neuroimaging into being considered a big data science. Whereas genomics used to be a big data science when, a number of years ago, we've now caught up, and in some cases may have even surpassed the amount of data that you can collect through genomics, for example. But before we go on, I want to drop a little fun fact on you. I'll come back to this at the end, and hopefully it'll kind of make sense. We have always kind of argued to ourselves that data expands to fill the available space for storage. This is something called Parkinson's law. Has anybody heard of this? It has nothing to do with Parkinson's disease. It has everything to do with how quickly, if you have a fixed size hard disk or storage capacity thing, that you will quickly fill that sucker up, right? No matter how big it is, you'll find a way to fill it up. And then you'll have to do the awkward thing of trying to delete old pictures and whatnot to make room, right? Well, it turns out that we've always kind of used the analogy that, oh, fish grow to the size of their enclosure. But it's actually not true that fish grow to the size of their enclosure. A fish in its natural environment will grow to whatever the natural size that fish happens to be, right? What happens, though, is it's the tank that constrains the size of the fish. I want you to drop that back in the recesses of your hippocampus for a minute. We'll come back to that in a little bit. I want to talk about the sharing of data resources. Now, Russ talked a little bit about this. I think you heard a little bit about this from Noah as well. While Russ was talking about some of the effects that he had noticed, I quickly whipped together this slide and dropped it in here. It may not be in quite the right place, but I wanted to share this with you because the very first publication I had as a graduate student was looking at that effect that was that sort of convergence of the initial study showed a huge big difference and that systematically got smaller over time. Let me explain a little bit about this because this is actually neuroimaging, believe it or not. Back in the 1990s, 80s, there were a number of studies which were really interested in ventricular enlargement in schizophrenia. So schizophrenia was kind of the idea at the time was that there was a type 1 and a type 2 schizophrenia. Type 1 was the more acute variety, and those people had smaller ventricles. And then there was the type 2, they were more chronic, and they had the larger ventricles. And back in those days, people didn't really have MRI scans the way we have them. They had CT scans on film. And so when people wanted to do a study of how big the ventricles were in schizophrenics versus controls, they would go and they would root through the files in the radiology basically the actual films and find all the schizophrenics, and they would measure the area of the ventricles as a ratio to the largest slice of the brain that would view and measure that as a proportion and multiply by 100. So you'd get some percentage of how much of the ventricles it took up. And then people would go and they'd have to say, well, now we need a control sample. So what are we going to do? people don't get CTs for no reason. So let's go and look at these people with headaches over here, and we'll use those as our control sample. Well, what happened is that there's a natural skew to that distribution of ventricular size. And anybody who had a particularly large ventricle size, but wasn't schizophrenic, people would hold their scan up to the light and go, Jesus Christ, you could drive a truck through those ventricles. There can't be normal. And they were trimming off the upper end of that distribution. So what happened? The distributions were artificially separated, right? So we see that in, some circa 1979 there when that first study came out, but systematically over time, as people got more sensitive to this, they got better controls, they were more kind of cautious about this, those lines kind of converged. So this was the very first study I published in the British Journal of Psychiatry. 20 years after we published this study, I had a student go work with me to go back, collect all the studies that had been collected since that time. We recapitulated this very same finding. But the other thing we found was this little thing over here. I don't know if you can see a pointer here. It's the one on the right. This is the graph of the ventricular size difference between schizophrenics and controls as a function of the number of authors in the paper. What do you think is happening right there? The more authors there are on the byline, the smaller the effect size. That blew my mind, right? Because that kind of says something about the next thing I'm going to talk about. So keep that in mind. But before we get to this other thing, I wanted to mention, so a number of the data resources that we see today, largely you can trace them, many of them, back to an early effort that I was involved in back a number of years ago, which was called the fMRI Data Center. We recognized that a lot of the study results that people were publishing in the cognitive neuroscience literature, the data that was used to generate them never saw the light of day. They were archived on somebody's hard disk, or they were stuffed in a drawer somewhere, and that there was an opportunity to gather that data, kind of package it, anonymize it, and do all the things that we need to do to make sure that PHI was protected, and bundle it and share it with the rest of the planet. We actually were funded by the NIMH and the National Science Foundation and the Keck Foundation in order to pursue this. And we collected data from, there were over 100 such studies, which I know may seem kind of small now, but it was quite large for its time, with 1.2 million files that were kind of part of this entire archive. And remember, this was kind of back in the day. And so what we did was we actually burned these studies to DVD, and we would mail them around the world. Now, you probably all are chuckling, right? Haha, isn't that cute? But keep in mind, this is how Netflix started, right? Is before Netflix became a streaming service, you would put in your order online and they would mail you a DVD, like watch your movie and then send it back. So this was right on point with the current technology. But we basically would put these in these little folders and send them out, and then people could use them to replicate or reproduce the original findings of those published research articles. This was a big deal. But very good, well-intentioned, right? So we reached out to a number of journal editors, we reached out to a number of colleagues to ask them, would they participate in this? Would you share the data from your studies with our archive so that we could share it with the rest of the planet? Everybody to our faces said, oh yeah, that sounds great. But then word got out and people lost their freaking minds. I swear to you, people thought we were taking their data from them. They asked questions like, whose scans are they anyway, and why should we give them to you? There were bylines like the prospects of data sharing gives brain mappers a headache. There were debates about whether or not we should even be sharing our fMRI data. So while you think it all just has always been, that is not the case. There were actually a lot of growing pains to sharing of data at all. And in fact, we had major organizations, one like the Organization for Human Brain Mapping. Many of you probably have attended those meetings or are members of that organization, had a policy statement about like when we should be sharing data. People said, maybe it's too early. We don't understand the bold response. Maybe we need to understand the bold response before we can share data. There was a whole lot of debates about that. But when you pointed out to people that, because there were so many excuses about why they shouldn't share data, one of which was my favorite was, my experiment is so complicated, I couldn't possibly explain it to you. And when you pointed out to people that, well, that means it's not really science now, is it? They got a little chippy. But there were other articles which came out that talked about good databases, bad databases, and ugly databases for neuroimaging, and it wasn't hard to understand which one they thought we were. Nevertheless, we went ahead and did that anyway. We actually were very successful for a number of years, but then the NIH, being the NIH, kind of cut off the funding and we kind of had to retire it. People ask me all the time, did the fMRI data center effort fail? And I don't believe that at all. I think actually it was like ridiculously successful because of all of the databases that now we see as a consequence of that. And frankly, all those databases have done it so much better than we ever could, which is a good sign that we started something that people picked up. Now, one of the main reasons why we were interested in starting this all to begin with was the notion that I think Russ talked about a little bit earlier, the notion of publication bias. Does anyone really know what publication bias means? Publication bias is that reporting of outsized effect sizes with ridiculously and unusually small sample sizes. And there's a database called BrainMap. Maybe some of you are familiar with it. It actually just records the local maxima that you would maybe ordinarily report in that table of local maxima and Talairac coordinates that might appear in your journal article. They just grab those and archive them. And we were curious whether or not evidence of this publication bias effect might be present in that kind of a database, right? Very simple because it's just coordinate based. So we just went and said, okay, show us everything that's in the frontal lobes in this particular database. And I don't know if you can see it up there in this kind of this upper quadrant. I don't know if my pointer is working for you or not, but all those little red dots are all the studies. I think there's about 70 of them or so. And we went and you can do a variety of different tests for the presence of publication bias and basically plotting sample size by effect size. And you get, in principle, you should get this kind of, if everything's working right, everything should be like an inverted funnel around the main effect size. And in this case, it was very splattered all over the place. This is one of the hallmarks of publication bias. And so our publication on this really pointed out that this is something that's important. But the sources of publication bias are kind of interesting because it's kind of multifaceted. There's often things like the rush to publish. So for example, if you're kind of doing that analysis as you go, the second you get something that looks like it's significant and, ooh, maybe this is kind of cool, rushing it out to publication. So getting out there before someone else does and getting scooped. Focusing on the least publishable unit, that is taking your data set and chopping it up in all sorts of little mini hypotheses that you can go and test the effects for and then attempt to publish those. So basically quantity of publication over quantity. Thinking about yourself and promotion and tenure and what it is that you think your deans are looking for to give you tenure and plumping up your CV in advance of any of those kind of career decisions and justifications for research funding. These are some of the motivators that, and it's certainly not a complete list, of why people go and publish all these things. You'll notice also that these are the significant results. So what's happened, right? We have a literature, at least in its early days, and maybe still continuing, of a bunch of large effect sizes with relatively underpowered or under sampled distributions that give rise to this publication bias. And when we started our fMRI data center efforts, that was one of the things we sought to avoid, as well as making sure that databases like COINS, XNAT, DataSpace, Human Connectome Project, ENDAR, and of course, Open Neuro, which many of you are familiar with, are able to be utilized. So again, this idea that we started with way back when I was a junior faculty member at Dartmouth College has given rise to a lot of these different things, which like after a rainstorm here in the Northwest have popped up like mushrooms over the last 20 years or so. But these are all things that many of you can take advantage of. Now, I want to reiterate something also that Russ talked about when he was referring to statistical power. Statistical power is one of those concepts when you're taking your intro stats course, it's sort of alluded to, and then you like plow forward with like fitting of regression lines and stuff. But it's actually, in our case, it's actually fundamental because it helps to dictate what sort of numbers of subjects you should be looking for in order to find the effect that you're hoping for. So Ideally, more subjects is good, right? Someone once said this to me, so I put it in quotes. More subjects is good because you can achieve statistically significant activations. You can avoid those publication biases, right? Instead of stopping short, you're going to basically sample more of the distribution and hopefully get a more realistic effect. It helps to ensure replication, as Russ kind of told us about earlier this morning, and optimizing that statistical power, publishing in top journals, et cetera, et cetera. So over the years, there are a number of articles which have talked about statistical power. I urge you to read these and take them seriously. Statistical power shouldn't be a mysterious kind of a concept. It should be one that is sort of second nature. These articles advocate for making sure that you get an adequate sample size, right, for the effect size you're looking for. The thing that's Russ talked about with this study by Merrick and colleagues was that this notion that you need tens of thousands of individuals to be able to do any sort of brain-wide association test. This caused panic amongst your generation who are coming up in the field about, oh my God, do I really need to find 10,000 subjects in order to test anything? Or people who are like lab directors wondering about how they're going to write that particular grant to justify 10,000 individuals. I think that's been overblown, and I'm hoping to kind of like tell you a little bit about that. Oops, sometimes. So firstly, let's do a little bit of statistical review. The statistical power of a test, as Russ kind of reminded us, is that measure of the ability of an experimental design or hypothesis testing arrangement to detect a particular effect if it's truly present. This comes from something called Neyman-Pearson theory. Jerzy Neyman and Egon Pearson were the ones who came up with this. Does anyone know, does the name Pearson ring a bell with you? Why does that ring a bell with you? What? The correlation coefficient? Do you think this Egon Pearson invented the correlation coefficient?
All right, one sec.
I guess not. I'm going to keep going. So this is his son. So Carl Pearson was the one who came up with the Pearson product moment correlation. This was his son, who was also a statistician and also worked at University College London, where I got my PhD. So kind of interesting. And by all accounts, Egon was a much nicer guy than Carl. For whatever that's worth. But anyway, he worked with Jerzy Neyman, and they came up with this idea that we were all very familiar with about setting up of an alpha level and correctly rejecting the null hypothesis. We want to make sure that we minimize that if we actually do reject the null hypothesis when the null hypothesis is true. We've made what kind of an error? Type 1 error, right? That's our alpha level that we fix. The other side of this little matrix is when we don't reject the null hypothesis, but the null hypothesis is false. This is a type 2 error, or referred to as beta in this, whereas alpha is like your significance threshold. Beta is that probability that you will incorrectly accept the null hypothesis. 1 minus that is your statistical power. And that is a function of the effect size, and it's a function of the sample size. So those are two key things. You can think about this by looking at some distributions where you've got, say, here is your kind of control condition in red here. It has a mean of about 10. You've got some alternative, which has, say, in this case, a mean of about 17. You've got some alpha threshold that you want to exceed. It's this area next to whatever your critical value is. To the left of that, 1 minus that is the power of that test. And it is a hallmark of a relatively well done experiment that has sufficient power to find the null hypothesis when reject the null hypothesis when in fact you should reject it. You can go and do these calculations yourself. I encourage you to do this. You can use something called the non-central F distribution if you really care to know. It involves the calculation of something called a non-centrality parameter, which is based upon that effect size estimate. Russ mentioned Cohen's D. In this case, I created these curves and I used something slightly different called a Cohen's F squared, which is a little more generalizable than a D because it works for multivariate analyses like multiple regression and omnibus F tests, for example. And I can set the value and I can set my degrees of freedom. In this case, it's like I have two things I'm doing a comparison against. So I have 1 degree of freedom. And here's where I have an effect size of 0.05. Here's 1.1. These are not probabilities. These are the kind of the scaled effect size estimates, and all the way up to 0.3 in this case. And you can see that as that effect size gets larger for any given sample size, I have the ability to detect that more frequently, given my statistical power, which is on the y-axis. I can go and adjust all sorts of things like the number of degrees of freedom. So this is how the curves change. If I say instead of degrees of freedom is 1, I have numerator degrees of freedom equals 2, and then likewise here's 3. And you can see how, okay, as I go from, say, a very small effect size, I need many more subjects in order to get the same amount of statistical power than if I have a very large effect size where I don't need that many subjects. Is that all clear? A little bit of remedial statistics for you that you might have slept through back in, Stats 101. Now, you can go and do this little experiment, taking that same code that goes and generates that non-central F estimate of your statistical power. You can download data, for example, like emotional faces task activation data from NeuroSynth, or any of your other favorite purveyors of statistical results images. Download those and actually scale your data such that it's on the same scale as an effect size estimate. Now, this is a little bit of a cheat because effect size estimates you're not really supposed to draw from the literature, but you kind of need to get it from somewhere, and you can't just necessarily make them up. So where would you get them? You'd get them from the literature, what's been published or what's freely available to you. So I recommend doing it, but keeping that caveat in mind that you want to be a little bit careful because it's probably biased upon publication. People publish only publishable, significant results. Nevertheless, you can go through, and in this case, I went and did I set the Cohen's F value at 0.3, and I walked through a number of different scenarios, if you will, of sample sizes from 50 to 200, looking at statistical power fixed at 0.8, 0.85, 0.9, and 0.95. Keeping in mind that what that power estimate is telling you is that, in this case, 0.8, 8 out of 10 times, if I had randomly reproduced this experiment, I would expect to find this result. At the next one over, this is at 0.85, so 85% of the time, etc. Whoops.
You're supposed to do it.
What happened?
I think it might have just been the cord got bumped. No,
I'm not sure what to touch. I don't want to break anything.
it used to like very.
Screen sharing has stopped because the external display is disconnected. I bumped the wire. You back?
Okay, that's fine.
Okay, I'm so sorry, everybody. Can you see?
Screen share.
Uh-oh. Oops. I'm sorry. No. I didn't hit it that hard, I promise.
Yeah.
It's really fickle.
Share.
Share screen 2.
This one.
Oh,
this one.
yeah. I think you need to start presentation.
Oh, no.
Yeah. Sorry.
Okay, sorry, everybody. I bumped the cable, which is don't bump the cable. That's the message. Because the external is disconnected again.
Okay.
Oh. Okay, I'm gonna try not to bump anything again.
Start sharing again.
Sharing.
Oh no, it doesn't see the second screen again.
Okay.
Hang on. Actually, leave Zoom. It's gonna be a problem again, I think, the thing that we had before. Let's try this.
Okay. Sorry, everybody online.
Leave this sharing thing for a second.
Okay.
And then leave Zoom.
Leave Zoom altogether.
Yeah, leave
Oh.
that
Okay.
and then come back. There.
Do I have to do all this video stuff?
Yeah, you can do the video thing. Or you just just hit the video to.
Okay, there we go.
Land and then
Share sharing.
Doesn't see the other screen.
Oh, man, this was really hard to get set up in the first place. I'm so sorry. Don't bump the cable, Jack. do you recommend here?
Let me think through all
Yeah, what did we
the
do?
cargo cult that we did.
What did we do? It was voodoo and magic to make it happen, and now we're trying to remember what that
Sorry.
was.
Close this interface for a second. Um,
Didn't we have this problem before the last time I gave a talk here?
uh,
Oh, here we go. Let's try this. No, it doesn't like that.
Leave it again.
Leave Zoom.
Yeah.
What's the deal?
It's not seeing the second monitor.
No.
It has, oh, you don't have a second monitor. It's mirroring right now.
Oh, maybe when we redid it, it
What did
decided to.
yeah, to only have one monitor.
So let's see, go back to my
PowerPoint.
PowerPoint. Automatic presenter view, that's what we had before,
Yeah,
right?
try presenting now.
Next slide.
Okay, now it has a second monitor, and now we're gonna go and leave Zoom again. I know this is weird, but we're gonna do
This
that.
is so weird. Right.
There you go.
There we are. Whew. Okay. Gotta find it again now. Oops. There you go. Here we go. Oh, I can't see stuff now. Wait a minute. I can't see my presenter view. Wait, here we go. Okay. So sorry, everybody. Don't bump the cable. Don't do that. It's just bad. Okay, so anyway, you can go through and you can set up an effect size that you think you're going to find, and you can scale your data, and you can systematically see if you look across as the sample size increases or the power that you're expecting increases, it gets ever harder to find the basically stuff that's significant. If you then lower, in this case, your effect size to 0.2, a little bit more disappears, makes it a little bit harder. That effect size is getting smaller. And if you make it 0.1 in this case, it's smaller still, meaning that, 200 subjects is probably okay, but you're probably going to need more in order to be able to find it. So one can draw some conclusions about this. Now, where does this come in handy? This comes in handy in your grant writing. How many of you have written a K award? How many of you are going to write a K award? Oh, come on, more hands than that. Of course, you all are going to write a K award. All of your grants are going to expect some section that talks about statistical power and how you're going to justify the number of subjects you're going to need. You're going to need to do something like I just showed you in order to be able to help justify your sample size. In this case, I can make some sweeping, maybe wrong statements about my statistical power for emotional faces tasks. In this case, I can say that, oh, for an omnibus effect size of 0.1, and a p-value of 0.05, I would need a sample size of about 150 people, or about 75 per group, to have 80% power. That is an 80% chance of reproducing that effect for to detect a robust activations in the amygdala in this task. I can go through and make other statements about other different brain areas, for example, the fusiform face area or in cortical or frontal brain regions. And that can help me to justify how many subjects I need. I can then multiply that number by my scanner, hourly rate, and I can figure out how much I need to budget for my scanner. Of course, you can also do that in reverse. You can also figure out how much, basically how much money you have and how much power you could effectively be able to expect to get too. So it works both ways. Now, I should say that all of this seems perfectly reasonable for trying to determine your statistical power. However, I would tell you that a lot of the face processing literature is based upon sample sizes that were about 11 subjects. So instead of 150, a lot of the early studies, which were published in Science and Nature and various other top-tier journals, were based upon much smaller sample sizes. And yet they have become kind of the go-to for this particular literature. So let me talk a little bit about multi-site studies, because I think these are some that you're going to probably be working with the data from. Many of you are probably familiar with the Human Connectome project. When I was at the University of Southern California, we were very involved in the Connectome project, the Healthy Brain and Child Development, the HBCD grant. Maybe some of you are involved in that, either directly or peripherally. And the UK Biobank is kind of the current giant gorilla in the room in terms of like overall sample size. These are very large studies. There's a lot of data. There's a lot of richness there. They're very deep in the sense of trying to collect data on as many subjects as possible. I can't remember what the UK Biobank is up to now. I know that it's quite large, and I saw who went to OHBM recently. Yeah, Steve Smith, who won the Glass Brain Award. I was talking to him before that ceremony, and he mentioned that they are going to be going through and reprocessing all of their data from scratch to start all over again, because the technological wave of all the software and how like efficient it is and how accurate it is much better than when they started. So all of those hundreds of thousands of subjects are all going to be reprocessed here very shortly. So you can look forward to that. One of the ones that I've been involved with, and many of you are probably involved with too, is the Adolescent Brain and Cognitive Development Study. This is a very large multi-site data collection effort that has a very rich set of imaging parameters that they've scaled so that it works on Siemens, Philips, GE, et cetera. And they're able to collect a lot of different data types, T1, T2. They can get lots of fMRI as well as diffusion and a few other exotica as well. And I was interested in this particular study that was done by BJ Casey and colleagues. They were looking at an emotional end-back task, again, kind of riffing off the emotional processing kind of theme here. The thing that struck me about this is that when they presented their results, they didn't present them in terms of like a T-map like many others do. They presented them in the context of a Cohen's d effect size estimate map. So if you look at this, this is this map here is actually colored with respect to the Cohen's d effect size. So that is a standardized difference between your two distributions in terms of activation. Here's some like general accuracy related behavioral statistics. But when they presented or distributions, when they presented their brain activation data, they did it in terms of Cohen's d. So this made it kind of convenient. One of the things which is interesting is that the max and the min on the Cohen's d color scale that they presented was about 0.6. We just heard from Russ that that kind of optimal level of an effect size estimate of Cohen's d is about 0.6 or maybe slightly north of that. So they also, in their study that had 517 subjects in it, was reporting results at a value of about 0.6. This actually is very convenient because I can go and take that Cohen's d, I can work it backwards with fixing my statistical power that I want to have, and I can find out for any of those colors that are in that map about how many subjects I would need to reproduce that particular pattern of brain activation. So this little table down here, apologize, it's so small. The critical bit is this bolded kind of line here. So for things that have a color in this map of yellow and a value of 0.6, you need about 40 subjects in order to be able to have statistical power to be able to reproduce that effect. So anything that's yellow there, you don't have to work that hard to get it. You need 40 subjects. However, if you go down to things that are slightly below that at about 0.3, you need 140. subjects. Call it 150, right? For sake of rounding up. So it's 150 subjects. That becomes a little harder, wouldn't you say? So those areas that are maybe adjacent to some of those yellow ones that are on that color scale, you're going to need more subjects to be able to find that as a statistically reliable result. Then if you go down even further, this like darker red, about 0.2, you're going to need 327 subjects. If you go down even further, and the ones that are sort of in black are really close to it, of an effect size of about 0.1, you're going to need 1,300 subjects in order to find effects there that are reliable 80% of the time. Think about that in terms of money. 1,300 times $600 an hour nominally for your scanning. That's going to be an expensive bill. So you have to start asking yourself, okay, how hard do I want to work to be able to find those effects? Kind of interesting. Another study was done by Steve Smith, who we just mentioned, and Tom Nichols, who many of you are probably familiar with, is a kind of statistical guru in our field. They did some examination of the UK Biobank. They looked at, firstly, they did some theoretical power calculation curves, similar to what I did, but they did something a little bit differently with how many subjects they needed up the y-axis here, and the number of statistical tests that were being performed. So the curves I showed you earlier were only really based upon one statistical test that you were doing. If you're doing multiple statistical tests, you need to correct for that multiple comparisons problem that you've afforded yourself there, right? So they're attempting to then fix 80% power, but at these very tiny levels of variance accounted for. So this blue line here is 1% of the variance accounted for. 1% of the variance. That's tiny, right? 0.1% of the variance is this like orangish reddish line here. 0.1% of the variance. And here, 0.01% of the variance is this yellow line. And this K is the number of tests, and this N is the number of subjects you would need. If you are really worried about finding a variance in your regression model, finding a variable which has 0.01% of the variance explained, you are going to, and you're doing as many voxels as in your analysis that you're going to be doing, you're going to need something like 395,000 subjects. Now, maybe you're the UK Biobank and you can afford to do that, but for the rest of us mere mortals, that is really, we can't do that. Another thing that they did is they again did a faces, shapes contrast from their UK Biobank data. This included 12,600 subjects. So when you do a statistical analysis of 12,600 subjects, what happens? Well, pretty much the brain is significant, right? Everything in the brain lit up. This upper image up here at the top, this is the percentage of signal change. What's interesting about this is already thresholded. So statistically thresholded, they went and chopped it out at some level that the Bonferroni corrected level of 0.05. This was across 1.8 million voxels, and only 19% of those voxels actually did not survive the thresholding. So everything that's left is all statistically significant. So now you're left with, how do you interpret this, right? Well, you might try correcting for certain variables and whatnot. So you attempt to adjust for sex. Well, then pretty much everything disappears except for a few different key areas. Well, that's great. But what about overall head size? Men and women on average typically differ by the size of their craniums, right? And so if you attempt to correct for that too, now you've got a problem because sex and head size are going to be themselves correlated. And now it's going to be very difficult to interpret how this particular, what's the effect that's driving this? Is it head size or is it sex? Is it based on your sex chromosomes or is it based upon the size of your melon? It's very difficult to work this out. One thing which is kind of interesting about this is that the maximum Cohen's d effect size that was achieved from this was 1.57. This is more than twice that 0.6 value that Russ talked about. And the minimum, interestingly, was, hold on, I want to make sure I get this exactly right here. Of the results that are shown here, the minimum correlation that they claimed was detectable was a correlation value of 0.049. Square that value, that's the percentage of variance you're attempting to identify. 0.049 squared, right? It's about what, 0.2%? That's tiny. And Apparently, they needed 12,600 subjects to be able to find that. Again, you need to start asking yourself whether or not some of these things are necessary. And of course, if that wasn't enough, they went and correlated things with 14 million univariate association tests between these imaging-derived phenotypes that come out of the UK Biobank and their other brain imaging variables across the 14,000, in this case, 500 subjects. And the thing that which is interesting about this is that irrespective of what's done here, you'll notice basically they did this like a genome-wide association plot, but these are basically the behavioral variables along the x-axis, and then these are the like Bonferroni corrected kind of plots. There's multiple of them depending on which imaging modality it came from. So there's 7 different imaging modalities they're testing here and whatnot. The thing that's interesting was interesting to me is they did approximately 100,000 associations over 5,456 variables were FDR significant. 15,000 of them were Bonferroni significant. And the minimum size of the variance accounted for was 0.1% of the variance. Again, you have to start asking your question. Do you really want that 1.1%? Because you're going to have to work for it, and it's going to be very, very expensive. Now, for some of us, when we're drawing from those data sets that have been made publicly available, bless the hearts of those people who've shared that data with us, because to collect it de novo would be, in this climate right now, for research funding, next to impossible. Next to impossible. Now, one of the other things about statistical testing, which my statistical colleagues at UVA have tried to urge me to think about, and maybe you can think about this too, is something called second-generation p-values. Second-generation p-values is sort of a misnomer because it's not really a p-value, but let me explain a little bit about what it's trying to do. Firstly, I should say that the software tools that we've had to work with for the past 30 years or so, SPM, basically getting started in the 1990s-ish time frame. JB will correct me about when it got started. And FSL tools that are really being used quite heavily in the UK Biobank are all predicated on looking at the general linear model. Everybody familiar with the general linear model, no question about how you're working to solve that. But one of the things about SPM was, at least in its original development, was geared towards finding stuff. It would almost be impossible to do an SPM and not find a statistical significant result. We have increasingly depended on tools like this to do most of our work because they're all trying to do a point hypothesis test of an observed parameter with respect to that parameter's value being 0. And so all these tools, an increasing number of open source tools, whether it's Python or R or whatever your favorite language happens to be, they're all based upon that point hypothesis idea that you're testing whatever your parameter is against a parameter equal to 0, right? And then making a probabilistic inference on it. In second generation p-values, this has become kind of a hot topic amongst the statistical theorists. That is, instead of having a point hypothesis, you have kind of a range hypothesis where you're saying that this middle of my distribution, in contrast to a single point of z equals 0, z of, say, a range from, say, negative 0.25 to positive 0.25 as being your exclusion region. Anything which falls in that little chunk, you disregard. And really what you're doing is you're fitting, I don't know if you can, if is my pointer showing up? I don't know if it is or not. This little red distribution here is the statistical error around your parameter estimate and asking whether or not it overlaps with this little region of exclusion. And so you can kind of see how this would be like your point null hypothesis. You traditionally have this fixed HO, but here, if your null hypothesis has a range, you can calculate some degree of overlap with the variance of your parameter estimate with this estimate that you have set as an exclusion zone. If it's totally separated, you've got full evidence to suggest that you've got a statistically significant, statistically meaningful result. If it overlaps a little bit, you may say, well, wait a minute, there's some evidence to suggest that they overlap and I'm not as confident as I might be. This has become kind of a hot little thing in the statistics literature. So my statistical colleagues and I had a graduate student go through, once again, download from NeuroVault some results images and perform this operation. So they went through and when they performed this second generation p-value, it tends to clean things up a little bit more. One of the benefits of this is you sort of get an effect size estimate and you're kind of accounting for your statistical power all in the same thing, which is kind of convenient, and it does help to threshold things a little better and make things look a little cleaner. This is just an early version of this that we pursued, and so maybe one of you could take it on as a project. It might be something worth something to you to look at these second generation p-values as a way to improve your inference, your thresholding, and therefore your interpretation of your results. Now, one of the things I've begun to ask myself is fMRI itself enough to be able to help describe brain activation? Perhaps we need to do something different, right? Doing just statistics upon statistics upon statistics and reifying p-values, actually, we may have tapped that vein dry. We might need to be thinking about something else. Again, the GLM, the general linear model, is a statistical model, which actually predates any neuroimaging, right? It goes back to the turn of the 1900s, right? It's a very old methodology developed by the greats like Fisher and Pearson and various others. They started that. But functional connectivities studies, they're dependent upon these region-to-region correlations. We mentioned Pearson before. We do more correlations on any given day than Pearson did in his lifetime, right? We are really abusing the Pearson product moment correlation coefficient. Egon is feeling very sorry for how we've abused his father's statistic. And so, like causality, though, just because something is correlated does not mean it's connected. And we need to be a little cautious about that, because sometimes that also affects how many subjects we might get in our particular study. So attempts to do, also, this is another aside, I don't know if you've noticed this, but I'm a little kind of just dissatisfied with how these studies get done, where you've got your correlation matrix of functional connectivity, but then you've got your structural connectivity matrix that you've gotten from DTI. People will go, they do all the network statistics, they basically do Olaf Sporn, every statistic in Olaf Sporn's book, and they try to correlate them with each other, and it never quite works out very well. Have you noticed this? Maybe it's only me, but the correlation is never quite as strong as you'd like to think it is, that structural connectivity and functional connectivity actually look alike, that if you have one, you have the other, but they don't. It's really kind of strange, and maybe that means we need to think a little differently. While wildly popular, and I'm going to talk a little bit here in a slide or two about machine learning and stuff, I'm not going to go into any more detail than I will, because you're going to be hearing about machine learning, and there's plenty of people who are smarter than me about it. But I want to share a little thing with you, which I think is kind of an interesting cautionary thing we need to keep in mind. And then my last thing I'm going to leave you with is, how can we actually take some of this data, use those parameters, instead of making statistical statements, can we make model-based statements on them that are beyond the general linear model, to put things into motion, to take advantage of time, and maybe develop things that look like digital twins, which I think is a very exciting area that we're in brain imaging, we're really poised to take advantage of. So here's my comment on machine learning. Take this with the spirit, which I mean it. I am an editor of the journal Neuroinformatics. I'm the editor-in-chief. I get papers every day, which seem to be, it's weird. It's spooky weird. They like follow this same recipe always. And I want to bring you guys just your attention to this, because I want to encourage you to avoid doing this, because it drives me bananas, because I see these all the time. I get these studies and they are almost exactly the same. They come from overseas. I won't point to any particular countries, but they must all take the same class or something. But they're always the same formula. Disease X, throw me out a disease, any neurological disease you want. Pick one, any one. What? Parkinson's disease. Okay. Parkinson's disease is a worldwide burden on patients and clinicians. Clinicians are overwhelmed. They can't diagnose Parkinson's properly, and so they are overwhelmed. But early detection is vital for Parkinson's disease. So we downloaded some data on Parkinson's disease from some random sketchy place on the internet, and we propose that a machine or deep learning or AI model is needed. So we insert our highly complicated Rube Goldberg, really weird looking machine learning model right here, and we force our data through, and we go and calculate area under the curve. We look at F1, we look at all the different statistics and come up with that big statistical wall that every study like this has. And we say, and all of our metrics are near perfect. Russ talked about things that were like 100% or whatnot. And they claim that they're doing as well as classifying cases as, no one better than anybody before in Parkinson's disease cases. So therefore, these results indicate that our method may be useful in diagnosing Parkinson's disease. Ta-da. And I see and they follow just insert for X here, your favorite neurological condition. They're all doing the same thing. And Russ told you that anytime you see something that says, oh, we got 100% classification rate, you should be very, very cautious. Very, very cautious indeed, because it usually means somehow they screwed up. There was some leakage. They didn't really have any sort of split half. They didn't do any of that stuff. The thing that bothers me in particular about this is that the authors of whatever study they downloaded their data from or whatever, they didn't need their algorithm to classify those subjects as having Parkinson's disease or whatever. So the utility of your particular methodology really needs to be couched in you're making an incremental improvement. And if the original authors did not need your algorithm to make their prediction, then they probably don't, they don't need it, right? It's not an incremental improvement. So I'm a little cautious of this type of thing because I swear to you, I will see 20 of these types of studies exactly written this way this week. And I will reject all but one of them. I will not send them out to review because they're atheoretical, and frankly, I think they're ascientific. I just really don't like them. And I hope that you guys will avoid following this particular recipe. Now, I should say that I am a fan of applications of AI and machine learning in the right context. And one of the things I've been particularly interested in are things like from this natural scenes data set that come from the folks in Minnesota. This is not a very deep data set. This is actually a very short data set, but it's very wide, right? It's only got 8 subjects in it, but those 8 subjects were scanned like across multiple different scanning sessions on like 30 to 40 different scanning sessions, looking at naturalistic stimuli. So this is pretty cool, right? So a study in particular was this one by Tagaji and Nishimoto, which I think has been published now. It was in bioRxiv at the time I found it, looking at high resolution image reconstruction with latent diffusion models of human brain activity, drawing from this particular data set, which is really cool. So there was the article. They fit a latent diffusion model for this, and they have these stimuli drawn from the naturalistic stimulus database, where you've got teddy bears, like a park scene, an airplane, like a ski slope, a bell tower, and I guess that's a train, right? And running it through their algorithm using the neuroimaging data, they can reconstruct what they think that pattern looks like, which I think is pretty cool. Here's this bit, which I didn't pop in right, but they can use basically the pattern of activated voxels to predicate which of the stimuli it thinks it's looking at. So it's a little brain reading kind of experiment, but it's brain reading in a particularly interesting way because of the depth of the naturalistic stimuli. So you could imagine how this would be really cool. There's a few videos on YouTube, if you care to look them up, of these kind of brain reading experiments where you basically are having the brain kind of using the brain data to interpret what people are looking at. And you get these weird sort of dreamlike, almost like those diffusion AI movies that get generated of like, weird things. It's really interesting. So I really like these studies. I think there's a lot of power to them. These ones where you're trying to do some sort of diagnostic classification, I really have an odd feeling about those, that somehow those are going to come back to bite us somehow. So I want to just warn you about that. Now, in my last little bit here, I want to talk a little bit about the development of mathematical models. Now, many of us, because we're using the general linear model, for many of us, that's as mathematical as we care to get, right? Once we've determined that, we've got an input variable, we've got a parameter, we multiply that parameter by the input variable, we get a prediction. That's good enough for us, right? But I've been very excited by some of the stuff that's coming out of Australia with James Pang and Mike Breakspear and Alex Fernito and colleagues about the fitting of these things called the Helmholtz equation models. These are really interesting because these are a partial differential equation, which all you need to know about that is you're looking at a little tiny little piece of space, and you're looking at that over time, and you're asking, how does that change fluctuate as a function of time and space? And with that, you get a wave. It's a form of a wave equation. And so you actually have these cascading waves of activity that once you stimulate one particular brain area, it actually cascades over the cortex. They've done this notion of what they call functional eigenmodes. So if you're familiar with the notion of a Fourier transform, where you're basically summing up a bunch of weighted sinusoids, this is like that, very much like that, but it also takes into account space. And so you're looking at traveling waves over space. This is really cool because I think we all kind of believe that these activation maps, these static activation maps that we produce from our statistical models, are like some sort of like, this is what a snapshot of what was going on, right? But we're not looking at the dynamics, and the brain is everything. If it's not, it's nothing rather, if it's not a dynamic system that depends upon space and time. And being able to like look at models like this, I think is really kind of exciting. I'll show you a little bit more here in a second. Now, considering models, let's take a look at the shape and the structure of the Helmholtz model, which is up there in the corner. Take a look at that. So I asked a colleague of mine who's a particle physicist. I said, this is kind of where we're at. Here's our current state of the art with partial differential equations. What is the current model for particle physics? And he was kind enough to send me this slide, which is the current model, the standard model for particle physics. And this is their partial differential equation. I am not going to try to explain this to you. This is only for shock value about putting this up here. But I can assure you that any of these little terms in here, a particle physicist can spend their entire career working on. And so this is the standard model. And each one of these little chunks here kind of accommodates a particular thing out of the model of particle physics. We are nowhere close to this, but I think that with some judicial thought about this, we could actually build a proper representation. Now, here's kind of how I've started to do this. Maybe this is of interest to you, or maybe it's not, but I've started to think, going back to foundational neuroanatomy, about how we build our models and how we might be informed by some of those basic parameters. So y'all remember axons. This is all, stuff that you learned about in your neuroanatomy courses, where you have, there's the axon comes out of the cell body, out of the soma, and it's wrapped with the myelin sheath, et cetera. The thickness of that myelin sheath helps to govern the speed of transmission of those neurons. Remember that part, right? They're kind of interesting. And these are all bundled, and they create the fasciculi and the different connections between brain regions that connect one cortical area to another cortical area. Of course, where this kind of got its foundation was in the study of giant squid axons by Hodgkin, Huxley, and by Eccles. And they created something called the cable equation. This is foundational stuff. You'll find this in any intro neuroanatomy book, especially computational neuroanatomy. There's something called the cable equation. And the cable equation takes this form. It's a partial differential equation. Don't let that intimidate you. Again, it's talking about a wave of activity happening over time, over space. That's all you really need to know. And basically, they were the ones who found the action potential based upon this particular model. And this is how they modeled it, with the function of the channels opening and closing, creating that electrical depolarization, and creating that traveling wave. They won the Nobel Prize for this. So they must have been pretty good, right? But the cable equation actually has its origins in something else called the telegrapher's equation. The telegrapher's equation comes from Lord Kelvin, who and his peer, James Clerk Maxwell. Many of you are familiar with Maxwell's equations, the famous equations that really govern electromagnetic interactions and kind of govern how like our cell phones work and all that stuff. Very important. But it was Oliver Heaviside who took those equations. He took Maxwell's equations and turned them into the form that we have them today. But he also conceived of this thing called the telegrapher's equation. The telegrapher's equation solved a problem of transatlantic telecommunication. When people tried to send using a little telegrapher's key to try to send a message from England to Washington, D.C., it got distorted, it got smeared, it got delayed. It was through his solving of this equation that solved that problem and gave rise to telecommunication. Hodgkin, Huxley, and Eccles took this equation, they modified it slightly, gave it a new name, and won the Nobel Prize. So it worked out well for them. But taking that idea and asking a question about that degree of myelination around that axon, think of it as if it's an insulated cable. You've got a core of some material that transmits information. You've got insulation around it to help protect that signal from other interfering signals. And the more insulated it is, the higher fidelity you're going to get. It turns out you can measure this very property, this notion of the inner diameter of the axon to the outer diameter of the myelin sheath in neuroimaging. I'll show you how you do that. But that ratio is referred to as the G ratio. And it turns out the G ratio has a sort of an optimum ratio. I'm going to tell you the answer. The answer is 0.6. If you know the inner diameter of the axon and the outer diameter of the myelin sheath, the value that you want to achieve is 0.6. The actual value is 1 over the square root of E for anybody who cares, but 0.6 is probably pretty good. So if you know that value and you know what about the G ratio is, you can take diffusion imaging, you can take T2 imaging and T1 imaging, you create a T1, T2 ratio, you can do a little bit more magic, and you can actually get a G ratio image. And that's what's down here in this lower quadrant here. So basically you're combining multiple image types to produce a ratio of the axon diameter to the myelinated diameter in every voxel of the brain. So it's sort of like FA, but it's actually much more informed and neurophysiologically rooted, which I think is kind of cool. Here's kind of a bigger version of that. You'll notice also if you look in the central nervous system or the peripheral nervous system, this idea of this myelin sheath to the axonal diameter looks a little different in the CNS versus the PNS, but you get this kind of idea. And here is the map that you can produce that looks a lot like FA, but again is more physiologically kind of important. With a slight transformation of that G ratio, you can get a value which is proportional to conduction velocity. This was identified by a collaborator of Hodgkin and Huxley named Rushton back in the 1950s, and that if you do this little simple transform of the diameter of the axon times the square root of the negative log of G, you get a value that's proportional to conduction velocity. This is fantastic. This is a functional statement about a voxel location in the brain that's based upon structure. This really tells you that it's the property of the underlying tissue which dictates how quickly an action potential can cross that voxel. This is fantastic. We can use this. So my colleague Benjamin Newman has taken this and he's looked at our autism spectrum subject database from our Autism Center of Excellence effort. This is over 300 individuals. It's a little bit small, but in looking at the G ratio, he noted fundamental differences where there is in autistic subjects, there is slightly less of a G ratio, whereas in relative to normal controls, and this gave rise to slightly reduced conduction velocities in autistic subjects relative to otherwise typically developing children. What was also particularly interesting, and I'll draw your attention over here to the right side, is if you look at all cortical ROIs, there's still a little relationship there, but it's clear that there is a reduction in this overall conduction velocity correlated with social communication questionnaires that are really kind of at the heart of autism spectrum disorder. So this is kind of cool to be able to look at parameters like conduction velocity. So it's not some necessarily a statistical result of activation. It's a value that's more in line with precision neuroimaging, which I think many of you may be increasingly becoming familiar with. And finally, I want to wrap up with just a couple of things about what about N of 1 samples? So is it possible to do stuff with a sample size of 1? We talked about 10,000 subjects. We just talked about 300 subjects and a variety of other different ends of some substance, right? But what about a sample size of 1 person? Well, I did a study a number of years ago, which I think sort of has led me down this path. We started with looking at diffusion tensor imaging, and diffusion tensor imaging really has some interesting properties to it because you can make kind of a much more of a quantitative statement, in my view, about the degree of connectivity that connects multiple regions with each other. You can get a density of concentration of connectivity. And using a variety of different methods, you can kind of improve upon that. We've done this thing where we created this thing called a connectogram. Many of you have seen probably various versions of this. This is our version, which we like so much because it looks a little complicated, but once you get used to it, it's pretty, kind of comprising a lot of information. How this is arranged is everything that's in the left half of the circle is from the left hemisphere. Everything that's from the right half is from the right hemisphere. Things that are at the 12 o'clock position are the frontal pole, and everything that's kind of in the little wedge down at the bottom is basically where we dumped all of the subcortical areas. Each of the different little wedges, I don't know if this, again, I don't know if my cursor is showing up, but each of the little wedges represents a lobe of the brain, and each one of the little radial colored heat maps there is a reflection of a different parameter from a particular subregion within that particular chunk. And so we've got, here's a little atlas or a little key here. You've got different atlas spaces in this outermost ring. So we can look at different, whether it's the Destro atlas, the Campbell atlas, the Brodmann's atlas, et cetera. So we can compare multiple atlases against one another. We can also look at cortical morphometry in terms of volume, surface area, thickness, and curvature. We can look at node functional connectivity metrics. So degree, participation coefficient, community assignment, as well as look at different functional or structural things in terms of degree and participation. And then the stuff in the middle is represented the relative density color-coded by average FA over that particular thing. So in one snapshot, we're looking at a lot of information, and we've become quite fond of this particular representation. Our application of this was in looking in the famous case of Phineas Gage. Who doesn't know who Phineas Gage is? Oh, we'll talk to you later. It's a long story, but very famous case, one of the most famous cases of neurological injury in all of neuroscience. And in fact, you always see Phineas Gage represented in about the first 25 pages of any intro psych textbook you ever will lift up. I guarantee you. And in this case, we got CT data from his skull. We reconstructed his skull, and from a large database of otherwise healthy, normal individuals, we made him a brain out of those people. And we took every one of those brains and we fit it inside of his cranial skull, and then we threw tamping iron rods through it. So for those of you who don't know the story, talk to me later, I'll tell you the whole story. But for those of you who do, you remember that the tamping iron is about a 3-foot tall javelin-shaped piece of iron that flew up underneath his zygomatic arch behind his eyeball and out the top of his head. So that's the short story. Anyway, we were able to model the extent of his white matter connectivity, which was damaged by that, and then represent it in our little connectogram form here. So all of these lines are representative of those areas, those fasciculi that were basically intersected by the passage of the tamping iron, statistically speaking. So things that are more black, those were completely wiped out. Things that are brown were not as much affected. A couple of different things we learned about this is that it was only in the left hemisphere. It didn't cross over into the right hemisphere. That was controversial up until we did this. We also realized that while about 5% of his cortical volume was affected by the passage of this tamping iron, it was about 11% of his white matter volume which was affected. So again, about twice as much white matter volume as gray matter volume. So in as much as it might have been a cortical injury, it was very much a white matter injury. And so that was pretty cool. There have been a number of studies looking at fMRI studies of individual subjects. So this is a group study, but they did everything within subject. That is looking at that kind of motor stimulation effects. So like looking at people's wiggling of their feet or of their hands or of their tongue and looking at those different motor areas. Going and doing seed voxel analyses on each subject and looking to see what the degree of correlation was. Looking at patterns of overlap between patterns of activity, whether or not it was the foot area, the hand area, or the tongue area, the amount of overlap, and whether or not that was consistent within and between subjects. So kind of interesting. What's been particularly interesting is I was part of the Organization for Human Brain Mapping's Best Practices Committee up until a few years ago. JB Pauline, who you'll hear from soon, was involved in this effort, and a number of other people who are very much involved in some of the same work that we're doing here. And one of the things that was proposed to us, it was to come up with a set of best practices for these single subject studies that were done on the basis of clinical data. So my colleague, Susan Buchheimer, many of you may know her or know of her. She's a faculty member at UCLA. She is the person they contact to do these studies when someone needs to go in for neurosurgery, is to help do those analyses to make sure that no one's going to cut into any language areas or areas which need to be preserved. They try to avoid those. So the time between that analysis being performed and somebody going to basically be put under for anesthesia and surgery may be a matter of hours. In which case, you got to make a decision quickly and you got to be accurate. And so this paper came out maybe only a few months ago. If anybody is interested in the clinical applications of fMRI and the best practices for how you do that, I really encourage you to take a look at this, because for those sample size of one studies, it may not be that you're trying to necessarily make sweeping statements about how the brain with a capital T and a capital B work. You're making a very specific statement about how that brain works so that you don't cut anything that you want to keep. So very important. I would encourage you to take a look at that. And then probably the most famous N of 1 study, our subject is not here, and I don't think that it's a HIPAA violation to point out that this subject was Russ Poldrack. He published a study along with a number of others a few years ago where he subjected himself to over 100 different imaging sessions over about 18 months. And they did imaging, they did a daily survey to kind of record his mood. They did genetic analysis from blood draws. They did full RNA-seq related gene expression and ran through a number of different network analyses to look at how Russ's network architecture changed over time. All this data, incidentally, about Russ is available on Open Neuro. So if you're really interested in knowing a lot more about Russ than maybe you do now, this is an opportunity for you to go and do that and get really up and close and personal with Professor Poldrack. The final thing I'm going to leave you with is I've become very interested in this notion of taking these data, taking models like that Helmholtz equation or like the telegrapher's equation, which sort of inspired our interest in getting out that velocity parameter and creating things that are more in line with digital twins. That is taking that data and trying to create a simulation of that particular person, of that particular brain. It may not be representative of the population, right? I don't care about that in this case. I'm trying to have a fully high fidelity representation of a computerized version of somebody based upon real neuroimaging data that I can then manipulate. I can go in and I can say, give them a MS lesion right there and watch what happens. So things that look like this, is this going to work? Oh, I hope it's going to work. Here we go. These wave-like equations. We can produce patterns of activation. We can produce these traveling waves of activity, which I think are really exciting. So this is some further unpublished stuff from Mike Breakspear, which really kind of inspires me to be thinking about this. One of the other things I've started to do is really play around with what these things what the components kind of look like. So using the underlying data as a scaffold to superimpose on top of it simulated kind of things. Here's like one example. So taking white matter fiber connectivity and taking little beads and running them along the white matter fiber pathways as if they're little action potentials traveling down axons. So I don't know if you can see that up there, if it kind of shows up really well, but you can see you've got these little beads following those paths. If you go and you kind of wrap some anatomy around that as well, to give it some kind of anatomical context, whoops, here we go. There, you can kind of see them sliding along those particular pathways. I don't know if it's really clear, but it gives you an idea of how those things actually follow a trajectory. They're not just static white matter fiber pathways. They're information conduits. They're carrying information that when those action potentials reach the cortex, it's going to cause a change in blood flow. That's going to change fold response. That's what we're going to detect. How can we simulate that? If I go and I take a look at that wave equation kind of idea, and I make it a little more dense, a little more high frequency, I can get things which look like I've lit the brain on fire. I think this looks really cool. And then if I try to bring all this stuff together, whoops, let me stop that. I think I can stop that. Beg your pardon. If I try and bring all this together, this is the kind of thing you can do. For those of you who really care, I'm using the same software here that was used to animate the movie Frozen. which is, used by Pixar and other companies. And it's really fun to play with, because I literally can light the brain on fire. It's really cool. I can make it explode. So just to kind of wrap things up here, I think the brain is the most complicated object in the universe. We've only started scratching it. We're going that problem. We are going to need to collect more data. We're going to need to collect more subjects, but to a point. At some point, it becomes impractical, and those smaller effect sizes are going to be ones that, honestly, we have to make a business decision, right? Do we need to go and get those, because are they going to be helpful? But we're going to be in a position to be able to do modeling efforts like this, to be able to make inferences at the population level as well as at the individual subject level, and create these simulated versions of people that we can give diseases to in silico, not in reality, right? Which would be pretty cool. Couple more things here. That data set size has tended to increase with every technological advance that we've had. We will continue to see that. Every time an MRI physicist turns a screwdriver, we're going to get more data. We're going to have to contend with that. Rather, you're going to have to contend with that. I'm going to be retired, living over on my island over here. It's going to be your problem. But that's how they make their money. And somebody had asked about how resolution and both that kind of stuff, how all that factors in. We're going to need to be sensitive to that. Gathering more data to ensure that statistical power, absolutely necessary to a point. It may be that pendulum has swung so far that it's actually impractical now, because to do those studies is so expensive. We can't do them unless we do some sort of multi-site type thing. This claim to need these 10,000 subjects, again, might be a little exaggerated. So we want to think very carefully about that. Now, modest-sized experiments, ones that are of maybe a few hundred, or in Russ's parlance, maybe about 20 subjects per group, permit you to be innovative, right? If something doesn't work, you could fix it and go collect more data, right? If you're committed to 10,000 individuals, it becomes very difficult to say, oops, well, that didn't work, and then go collect another 10,000. AI or ML are likely our future, and I didn't talk that much about it, but honestly, I think it is. I think we need to get used to it. But again, I think there's some caveats there, and I'm hoping that you'll be critical when you read those articles to make sure that this just doesn't become a routinized kind of a thing. Oh, that's the way it's done. I want to encourage you to be innovative, but critical about those studies, because sometimes I think they send a very peculiar message. But improved models of brain dynamics over time and over space, and how that can be made to dysfunction, I think is probably something we really need to be thinking about as we think about our own standard model of brain activity. And now's really the time to integrate function, morphometry, connectivity, function, structure, genetics, all the things into common models, so that we can be more precise, more accurate, and we can make our predictions that much better. And the data will need to be as big as it needs to be in order to do that. One final thing is all these different efforts to chase p-values and historical dependence upon GLM and whatnot, just to reiterate that idea of you being critical, of you being innovative. Don't be the fish, is what I'm saying. Don't be constrained by your own thinking here that is going to say, oh, this is the way to do it. I really want to encourage you to innovate as you're doing your little mini projects later this week and the full projects next week. I think we need to think bigger, and I think we need to be smarter about how we use that data. Here's a couple of articles that I've written about data and how we need more theory, and how kind of data set sizes should be kind of scaled. For those of you who are interested in whatever happened to my fMRI data center effort, this is the contents of several large Tupperware boxes which exist in the basement of my home in Keswick, Virginia, and they are the relics of the fMRI data center effort. It didn't disappear, it just migrated to my basement, and I have about 4 million DVDs with data on them. Believe me, it's a ton, and my wife wants me to throw them away, and it's sort of like, I can't, honey, I can't. So anyway, thank you very much. I appreciate your time. Do we have time for questions, or did I?
Yeah,
Oops, I bumped the thing again. I'm so sorry. Yeah.
How, these types of approaches that are like, really exciting what you described about, yeah, this cortical morphology and then neuroanatomy driven analysis approach can be, expanded out to, yeah, how connectivity between multiple brains that is can be done.
Yeah, absolutely. Well, if the hyperscanning, I haven't done those studies myself, but those are really interesting, right? Where you've got two people in two different scanners and they're interacting somehow. Is that the way, that's what you're referring to, right? Yeah. So, I mean, that's so dynamic, right? Because the response from one person becomes the input to the next person, and you really create this interesting dynamic feedback loop. I'd be very interested to see how you could incorporate some of these traveling wave kind of ideas when you've got two people interacting together, whether you could get synchrony or you could get kind of lead lag relationships. I'd really be kind of exciting to explore those things. But again, that's not an N of one, it's an N of two, right? Imagine if you had like a little, cocktail party full of people. You didn't have scanners to put people in scanners. You could have a whole little conversation going on. It'd really be kind of interesting. Those are possible now. So, I mean, those are another frontier that we should think about exploring. I wore you all out. I apologize. I think we have a coffee break, right? Yeah, it looks like you might need some coffee break. If you want to ask me any questions, please do. I'm delighted to answer them. If you aren't familiar with Phineas Gage, I'm happy to tell you that story. In the meantime, everyone, have a really good NeuroHackademy. Okay. Thank you.
Thanks, Eric. And we will resume in 30 minutes.
30 minutes.
The same place.
I'm signing out.